Alrighty, welcome everyone to the third installment of the HBCD EEG Summer Series. We're starting a little bit well into the summer. Now it's officially summer, but we have a great set of speakers. I think we have 5 talks in total going into a little bit of August. But today, to kick things off, we have John Richards, who's a distinguished professor at University of South Carolina, the other USC, and Dylan Gilbreath, who is a postdoc now at University of Maryland, working with with Nathan Fox with the EEG data core, but before was a student in Arkansas with Linda. So anyways, I won't take more time. They're going to talk to us about some of the work that actually they have been doing with the HBCD data and source modeling. So help me welcoming John and Dylan. Thank you, everyone.
Okay. Well, I'm going to start. First of all, thanks everybody for coming. I hope you enjoy it. If you have questions, you can put questions in the chat, and if Dylan or I happen to see them, we'll try to answer them when you put them in the chat.
Upending the apple cart every few years. Yeah. I mean, we always point to physics, but there's good reasons why we point to physics.
Here, somebody's talking.
Yeah, thank you.
And when also, if you we'll make some time at the end, and if you want to contact me after, you can ask questions as well. So I have overheads on a PowerPoint, and we're going to go through them. Dylan and I will both be presenting, so we'll sort of go back and forth. Dylan is probably going to present more about the HBCD, and I'll present more about the source analysis. So she and I are working, and with Nathan also, to try to make this source analysis model work for the HBC data. Also, I'm going to start my slides. So if we could do share screen. Let's see. Share screen. Try that. There we go. So this is an outline of the talk. I'll also refer you to this article at the bottom by Stefania Conte and I. This talk is sort of how to explain this article using HBCD data. So Stefania's on the chat here, so she might answer some questions too if we need her to. Basically, we're going to talk about the source analysis of EEG, the HBCD MRIs and EEG, and the other things they have that can be used, and then about one of our projects to try to make the source analysis work with the HBCD data, so people could take this program that we're developing and use it to do source analysis. I think that's it. Let's go down. Dylan is up.
Great. So hi, everyone. As John said, I'm Dylan, and John's going to provide a more conceptual, high-level overview or source modeling, and I'm going to focus more so on how we can use our HBCD data specifically to do this source modeling. So as everyone here knows, the HBCD is such a wonderfully rich data set, and we wanted more HBCD users to integrate the source level information into their analysis. So what we are doing is creating a source modeling MATLAB app that will take the MRI and the EEG that is downloaded from Lasso to generate our source models. Currently, I've created a program that allows folks to mark the anatomical fiducials on the MRI itself more easily, and from this, it can generate the head models, which we'll talk a little bit more about further into the presentation. The goal of kind of this aspect of the project is for just about anyone to be able to create accurate source level reconstructions of the brain for whatever subjects or subset of subjects they would like to do so for. Can you advance? Can.
Oh, you want it down?
Yes, please.
All right, Cyrus, you have to tell me. Sorry.
So to ground ourselves a little bit, John's provided me with a list of everything we could possibly need to do source modeling. So to do this, you need information from all of the structure or the MRIs. So we need the T1, the T2 MRIs, and also the HPCD is providing us a diffusion weighted image of the MRI as well. And you need the functional information as well from the EEGs. So we have our task that the HBCD does. We have a FACES task, a VEP, and a mismatch negativity task, as well as a resting state. And the HPCD also provides us some MRI derivatives that will make generating some of our models a little bit more easy. Can we advance to the next slide?
This one?
Yes, please. So I wanted to provide you guys with a kind of an image of what the lasso interface actually looks like. So if you've played around a little bit on the HBCD website, you might have seen this before. So this is where you'll go and download your MRIs, and it also tells you where everything and what all the things are that are available. So you can get the raw T1 and T2s that'll look vaguely like this. I got these from the Baby Connectome project from around the same time frames that we're looking at. So they'll look roughly similar to this. And it also gives you derivatives. Next slide, please. Yes. So it gives you tons and tons and tons of derivatives, more than you'll ever need for the source modeling project in particular. But specifically, what it gives you is motion corrected T1s and T2s, and also it gives you a segmentation of the brain already, and it provides you like a brain mask. So typically in source modeling, you'll generate these yourselves in a software like FreeSurfer, but the HPCD does this for you. So this will be much, much, much quicker computationally. And kind of the main takeaway from this little bit of slides is that the HPCD is providing us everything that we need for effective source modeling. But before we get too much into that, I think John is going to tell you about what the source modeling actually is and what it means. So John, I'm done for a little bit.
All right. Here we go. So this is going to be the outline. By the way, on this outline, I'll show it and have the current topic back colored in yellow. So what source analysis? So this is an EEG. This is a picture of EEG on the scalp. I think this might be adult. This looks like a P1 at the back of the head, and then maybe some kind of N170 or N290, and then a later component, and finally something that's happening in the front of the head. If this were an infant, I would call that an NC. These things that are recording on the scalp are being generated in the brain by the brain. And source analysis is a tool to take the information on the scalp and our knowledge of the things inside the head and the electrical properties of a head to tell where these EEG patterns are being generated in the brain. That's what source analysis is. Let's see. How are electrical currents? I think I borrowed this from Stefania, so don't be surprised, Stefania, if you see this. Basically, what happens is there's a large pyramidal cells that are in the surface of the cortex, and they're all lined up in the same orientation. So they're all pointed towards the surface of the scalp. And if you have enough of these, if enough of these fire at the same time, they fire simultaneously, you generate activity on the scalp. So what we're showing here are the possible postsynaptic potentials that say sum up from a large number of neurons. If enough of these are being done simultaneously in a specific brain area, they form what's called an equivalent current dipole. This is the electrical current source, and that current source results in current on the head, and we can record the voltage between 2 points that's being generated from that current. So that's how you get EEG. You get ERP by doing EEG and then time locking the EEG to a specific event. So EEG and ERP are both reflections of probably postsynaptic potentials from pyramidal cells in the brain. Let's see here. The forward model. So I'm going to use the word forward model and inverse model or inverse spatial filter several times. And this is a schematic of what these mean. So basically the forward model is how do you get from inside the head in the brain to the outside of the head on the scalp. And this top line shows activity in the brain somewhere. Say this might be the fusiform face area. So this might be in response to seeing the face. The activity in the head in the brain is generated in cortex and in the gray matter cells. So those would be the sources of the activity. The characteristics of the head, the conductivity pattern of the different media in the head, give you electrical fields in the head, and then you have a set of leads on the scalp with respect to those electrical fields. And this activity in the brain results through these media and these processes to activity on the scalp. So that's the forward model. I'll also use the word, we may use the word lead field matrix. Lead fields comes from these are the leads and these are the fields. So the lead field matrix is a matrix of numbers that relate these things that are happening inside the head on the outside of the head. The inverse model is the opposite. What we're doing in the inverse model is we're taking activity on the outside of the head, scalp recorded potentials or scalp current, and then we have sort of the opposite direction. So we have them being recorded in specific locations. We have the electric fields and the sources, and then from the activity on the outside of the head going through this process, we can identify where the activity on the head is being generated. And so these two things together are probably what I would call, when I say source analysis, that's what I'm talking about. What is the cortical source of the EEG that's being generated on the head? I will use the term inverse spatial filter to describe this part of the equation. Later I'll show you. I won't show you actual equations, but if you multiply the things that are happening on the outside of the head, the EEG, times the inverse filter, you actually will get a set of voxels, and you'll get the corresponding electrical current values of the voxels inside the head that are generating that EEG. By the way, I don't have my chat box up, so I don't know if anybody's asking chat questions. I'm not sure how to make the chat box come up. Feel free to interrupt me if you have a question. So there are probably four things that this gets a little more particular. And, and this top row are things that the HBCD has. So they have EEG recordings. The EEG recordings, are like a faces task, a mismatch task, and resting state, and so on. They also have, or potentially have, the electrode locations of those EEG recordings. So each participant who has EEG recordings should have an MRI, and we can take that MRI and determine the positions of the electrodes from that MRI. They also have a structural MRI, and which in our case, we're interested in the T1 and the T2, and possibly the DWI. And then they also have a source grid. And the source grid is something that we set up. Basically, our source grid, we take all of the the gray matter voxels and call each one of those a potential source. And so we think that the electrical activity is being generated in these voxels, so that's the source grid. So this is HBCD. That's what's there. So if you have access to this, you could take your resting state EEG and all of these other things, and then do source analysis of the resting state EEG. What's going to be generated in this app, and what we do sort of offline professionally in all kinds of ways, is from these data, or from these sets of pieces of information, we can create the lead field matrix and the inverse solution and do source analysis. And so the program that Dylan is working on will do this. It will take the HBCD data and produce these pieces of information that can be used for source analysis. And we'll talk about, I'll talk a little bit later about what she might give you in addition to a computer program. We're in the middle of discussing that. All right, so next. All right, so the first thing, we'll talk about these four things: electrode placement, head segmenting, conductivity, not very much, and source model, not very much. So these are the four things that are needed. The first one is electrode placement. So how does the HBCD give you electrode placement? Good question. And this is Dylan, so go Dylan.
Right. So as John was saying, to figure out where in the brain the sources are actually coming from, we have to have a decent idea of where the electrode net is actually placed. So in reality, like our source modeling first step is the moment that the net is placed on the infant. And there's kind of two ways that we can do this. We can use those pictures that all of the site team works very hard to take, and someone who has access to those photos can mark those fiducials on a head. Or we can take an average electrode template, and in that case, anyone can use the average electrode template in the HBCD. So we're kind of playing around with both of those ideas. Next slide, please. So the very first step in all of this is, of course, selecting an appropriately sized electrode cap by measuring the head. The HBCD just uses a tape measure to figure this out. I've never actually seen the caliper method being used, which is what is in this slide. It looks a little intense. But this initial measurement is important for our modeling step for another reason as well, not just to have like a great cap and a great fit, but sometimes a participant will have an EEG, but that participant will not have an MRI as well for whatever reason. And what you can do in this case is you can use a different participant of the same age and kind of the relative same head size as a proxy MRI. And this proxy MRI approach to source modeling actually has really great results. I think John actually has a few papers about it. So if you have any questions about that technique in particular, John is a really great resource. Next slide, please.
This is for me. When I'm doing this, we have this thing that called the geodesic photogrammetry system, which I think now exists in Greg Reynolds' lab, maybe. Yes, Greg? Basically, we put the baby with the cap on inside this dome, and then we take pictures. There's 11 or 12 or 13 pictures. And from that, we have a program that then will take those pictures, and we can get the locations of each electrode in space, in a arbitrary space. And one of the things, I'll point this out a couple times, and just to highlight this, if you see where my little cursor is, that is the electrode number 17 on the net. And notice that electrode number 17 is not on the Bayesian where it's supposed to be, and it's slightly above. And that means that the whole net has been moved slightly up, and that means that the electrodes are over different part of the brain. So one of the things that we do in this procedure is we don't guess where that electrode is, and we don't look at an EGI list of where the electrodes are. We measure where that electrode is on that baby. So that's what we do in our lab. We don't have GPSs in the HBCD. We do something different. Let's see. I think it's still my turn. Yeah, still my turn. So here's an example baby, and I'm pretty sure that these are the same electrodes on the MRI of this baby. I'll just note one thing. You can see these two electrodes on the side right here. This gray one is supposed to be the right preauricular point, and the right preauricular point is actually lower. It's down in the middle of the ear. So this net is slightly above the sort of nominal locations. And that's faithfully represented when we put the electrodes on the MRI. So you can see the same electrode is at the top of the ear rather than being in the middle of the ear. That can have real importance for doing a source analysis. All right. Dylan.
So here we're kind of entering into the first step of the source modeling pipeline that we've coded. John, can you actually play that video? I think it should have like a little play button
Oh,
on
sure.
the
Yeah.
left-hand
Here we go.
corner. Yeah, there it is.
There we go.
Cool. So this anatomical fiducial app will allow you to register several different anatomical fiducials. And an anatomical fiducial is just kind of like a landmark point in the brain that we can use to orient where the brain is in space. So you just have to know where certain parts of the brain are in order to generate forward models and in order to kind of create all of the things that we need to create. And this, as you can see, it goes through a list on the right-hand side, and it will show you, that's what the picture on the right is, where these fiducials should be marked using an age-appropriate atlas template. And this kind of lets any user who maybe doesn't have a ton of experience with MRI to be able to kind of do this level of analysis. There are some apps that will let you do this, but a lot of them don't actually say, well, here's the anterior commissure, and you have to run several different programs to sort out what's being marked. And this will take all of the numbers and all of the locations in both millimeter and voxel space, and it will use those throughout the rest of the program. So you don't have to exit out or anything. Everything is very contained in this space. And it also allows you to orient it with the electrode markers. So John, if you'll advance the slide. Great. So these anatomical fiducials are important for identifying the electrode locations. Just anyone who's dealt with infants knows that they all have very differently shaped heads. No infant is the same. So you have to know what the head shape is to kind of know where the electrodes should be on it. And we can use these fiducials and MRIs to translate our electrode map back onto the individual. And I have another representation on the next slide. So here's a kind of another way of looking at all of this information. On the left, we have just our normal HGSN sensor cap overlaid on top of the T1 MRI. As you can see, there's a couple sensors. Oh, you can't see my cursor, but kind of on the top left part of the brain, there are several sensors that don't sit very cleanly on top. And that's not what you want, right? You want to have your electrodes laid over your scalp in a way that makes sense. So in the right, and we'll go through how to kind of calculate these models. I've used the anatomical fiducials to orient where the head should be and where all of our electrode locations should be as well. So the electrodes on the right are sitting more cleanly on top, and their relative positions look fairly correct. Next slide. I think it might be you now.
All right. So we have the second part of the source analysis is the head and the head segmenting, or what I'll call the head model. And I'll go through that. So there is this me? Is this me, Dylan? I have Dylan or John on here, one or the other. This will be me. There are different models that people use, ways to model the head, and I've listed three common ones. The first one is that modeling the head as a series of overlapping spheres. And this is bad. Don't do it. But it's easy because it turns out that the head model can be analytically computed with just simple equations, but it doesn't work. The second one, you can model the head as a series of overlapping compartments. The compartments are usually the skin, the skull, and the brain, and sometimes there's an area under the skull called the CSF. This one's more sophisticated, and this one follows the actual outline or the shape of the skull and the brain. So it's better than the spherical model, which it doesn't really fit the brain or the skull. This one is better than the first one, but it's not as good as the third one. A lot of people use this second one because it's easy to find the three compartments in the head. It's a lot harder to find gray matter and white matter and these other components. The third one models the head as a set of individual elements, and that's the one that I use, and that's the one we're trying to push on in the HBCD. This identifies the various components of the head, like gray matter, white matter, cerebral spinal fluid. It assigns conductivity values to each of those components and uses a mathematical procedure called the finite element method to get a solution for the forward model. Each one of these, the purpose of these is to create the head model that's going to be used in the forward model. I'm not going to talk about the diffusion weighted imaging part, just to say that you can also add DTI to these models, because it turns out that white matter and DTI FA values are highly correlated. So it's a way to improve the conductivity model of the head. All right, this is you, Dylan.
John gave a really great overview, so I'll be very quick. This is our spherical model. So this is the easiest thing that you can do. You can run it on like a 1998 laptop. But unfortunately, the brain, the head, and the skull are not perfect spheres, as John pointed out. So this doesn't give you a very great reconstruction of the brain, and we're not currently using it to do any of our HBCD stuff. Next slide, please, John. And then the next thing that you can do is you can model the head as a series of overlapping compartments. And this uses conductivity values from the T1 and T2 images of the skin, skull, and brain to separate them. A conductivity value, I'm not sure if we defined it, but when you look at a T1 MRI, there are parts that are more dark and there are parts that are more light. And the brain and the skull and the scalp are all pretty different in terms of like their luminance. So this methodology uses kind of how bright they are in the image to be able to separate them. That's kind of a simple way to think about it. And this is referred to as the boundary element method, or a BEM, and it gives us a numerical solution to our forward model. This method is really great, as John said, for determining what skull or scalp, but doesn't really take into account cerebral spinal fluid or gray and white matter distributions, which we all know will affect how the signal is actually propagating through the brain. So it's not the best method. It is the one that we currently have working in our pipeline, though, because it's relatively easy to do computationally. And John, I think you're talking about the great method on the next slide.
Yeah, so this is the method that I prefer. Basically you go through procedures to model or to identify the parts of the head, including the skin on the outside, the skull, the brain. This is imperfect drawing of gray matter and white matter. And so when you identify those, one reason that it's important to identify these is that they differ in their conductivity values. And what's especially important is you can see this was a picture of a T1. It's not a very good picture, but there's a lot of cerebral spinal fluid inside the inner compartment, and cerebral spinal fluid has a very high conductivity value. Electricity flows through the water ions of cerebral spinal fluid easily. Does not flow through as easily as some of the other in some of the other components. So one of the reasons that the FEM models are better because they're able to model the inside of the head and cerebral spinal fluid. And this is a picture. I can't remember if this is from Stefania or Greg or whoever, but this is a picture showing. But we have 10 when we do this with infant. We have 10 different media types, and there's a list to the side. And then this is a picture of adults. With adults, I think we have 9 media types. And so the results of this analysis give you a 3D MRI volume where each voxel has a number representing one of these types of media. So that's how the FEM works. This is a fast because when we get to detail, it turns out that in these programs, they don't take whole head MRI volumes. They take text files of digital numbers. And so one of the things that you do in this method is you use what are called meshes. And the meshes are in our case are tetrahedra and series of tetrahedra, and each tetrahedra. So a tetrahedra is this 4-point little pyramid, like where that pointer is, and each tetrahedra has a number that represents the media type. So number 1 might be white matter, number 2 might be gray matter, and so on. So the tetrahedra are generated from that MRI segment model. This was not on the list up above, by the way. So I'm going to go over this really quickly because we're not doing this in the HBCD program. We use a series of computer programs and custom MATLAB scripts to do source analysis. FSL, SPM, MATLAB, Field Trip, maybe some other EEG lab, and so on. And each one of these computer programs gives us one of these things. Like this comes from using FSL to identify gray matter, and then using a program called ISO2 mesh to create the mesh. This comes from FSL, SPM, and a whole bunch of other things. So we end up then doing the computations with a program from Field Trip. Field Trip is a set of computer programs for doing EEG, MEG, source analysis. That's what we've been doing. And Greg is on here, and Stefania's on here, and a bunch of other people have worked on this with me. There's another way to do this, and it turns out that there's a newer version of a forward modeling program called data.HBCD, and there's an alternative to Field Trip called Brainstorm, and Brainstorm does everything that we want it to do, and data.HBCD is a newer version of the program used in Field Trip. So this is John. Stefania and Dylan and I right now are taking our original work products from our pipeline and converting them into the Brainstorm model. And in addition, we probably will do this with the HBCD data, and not totally sure exactly what our products are going to be at the end of this for the HBCD data. But we could do the same set of structures, the same set of programs with the HBCD data. And this is, I say on this, skip quickly, not the app. So, and this is another piece of information about how to do this. And then this is just to mention that the diffusion weighted images give you values that allow you to compute differences in conductivity for white matter, given its FA values or other values that come from DTI. All right, now we're back to Dylan.
So I think here we're just orienting everyone on where we are in terms of like all of our different forward modeling methods. So John, I think you can actually skip to the next slide, especially for time purposes.
Okay.
So where we're at is I have integrated a lot of information from these open source softwares, Brainstorm, Field Trip, SPM, and I've streamlined it and I've also edited it to use infant values for computations. So a slight problem with some of these softwares, which I'm sure everyone knows, is that they're based on adult values. So you have to edit things just a little bit. So I've been working really hard on this and I've been able to create our BEM models, so our second best solution. And I'm working with John right now to create our FEM models. And this will all be integrated into one system. So next slide, please, John. And the goal of John and I's project is to fully incorporate all of these source modeling steps that we've discussed into a mostly automated pipeline. You'll always probably have to be able to do the fiducials by hand. I know that there are several programs that exist in the world. There's one that MNI has that will mark the anatomical fiducials for you, but in infants, it's always a little bit tricky. I've noticed that the MNI program always misses the ears. So these are things that will probably always have to be checked by hand. I'm also working on integrating these FEM forward models currently. And I think that's it for me.
All right. So this is the last part about the source analysis. One of the end products of after all the forward modeling is done, we compute the inverse spatial filter. And Stefania and I have used a program called a method called eLoretta to do this, and we do this for all of our subjects. And in addition to that, when I'm working with several collaborators, and I hand out the inverse spatial filter to the collaborator and some MATLAB scripts written by Stefania, and they can take their EEG data with these inverse spatial filters and the MATLAB scripts and do the source analysis. So they don't have to go through the gray matter, the white matter, the segmenting, the ISO2 mesh. Instead, you have one file and two MATLAB scripts. So it's I'm working mostly with graduate students and postdocs who do this, but it's something that could be done moderately easy compared to some of the other things that we do. So this again is the picture. So these are the things that the HBCD has. This is what Dylan is working on. Dylan is making she's doing things also to create the head model, but eventually the program will be able to compute the lead field matrix and some version of the inverse solution, and in order to be able to do this source analysis. So that's the part about source analysis. I want to take questions now. I also have some slides showing us a specific study that was completed in my lab, and it's not HBCD material because we don't have any of the HBCD material yet. We're working on that. But if you have any, this would be a good time for you to ask questions.
I have a question for you, John. When we were
Sure.
doing when we were working on infant source modeling, one of the things we were really most interested in doing was including in our meshes the fontanelles, and I wondered if you had considered that or done that in your modeling.
So I keep losing a little bit of the audio. So you're wondering what if we include the fontanelles in the source model? We
Yes.
don't include them specifically, but the fontanelles are places along the seams of the bones of the head that have not yet where the bones of the head have not yet joined, and so they leak EEG in a different they have EEG or electrical activity coming out in a different way than when it comes through the skull. So we don't model those specifically, but we do model the skull itself around those areas. And it turns out that there's either no skull along those areas or the skull is very thin compared to the adjacent areas. But that is an additional step that people could do, and it does have an effect, especially on EEG that's measured near those places on the scalp.
So if I'm understanding you, when you create your conductivity models, you do take into account the difference in conductivity across those skull regions?
So, well, basically, we're not specifically modeling the fontanelles, those spaces themselves, but
Okay.
across those spaces, the skull is thin. And so there's less skull. The conductivity is less because of the skull. Right underneath the skull is either meninges or cerebral spinal fluid, which has a higher value of conductivity. So if you completely took away the skull around those areas, then you would have the conductivity of that underlying material would be the conductivity for that area. That's a good question. Dylan may work on that. Other questions? Bill Pfeiffer.
Hey, thank you guys. This is great. I wish I got more of my students to listen in on this, but I know it's recorded, so that's good. I'm wondering if I guess I'm wondering a couple of things. Do you have any, as children get older, they're going to do a little bit more movement, including head movement, and then including sometimes displacing where those electrodes may be placed from the beginning of a study towards the end. Do you have any ways that you're going to think about interrogating that? Again, particularly as they get older, and have you dealt with that? Changing cap placement.
So anything that you can say, if you measure it, we can do it. The problem is that that's not measured in the HBCD. So what's measured in the HBCD is you put the net on, you arrange it around, and then you take a picture of where the net is at that point in time. So if the net moves, or if individual electrodes could move as well, then you would end up with a different source model at the end of the session. The only way to do that would be to take a continuous recording of where those electrodes are throughout the session. Or if you know that if you're doing have a session and you know that the electrodes have moved so dramatically, you would probably just not use that infant. So that'd be a case where, the data that are coming in at the beginning of the session when you take those pictures does not represent what's happening during the session.
Which I guess if we noted that it happened, that may become part of the protocol to at least take a picture at the beginning, at the end, to know that you might be dealing with something like that. But you're right. I guess that
you could do that. The problem. So EEG. By the way, the output from this analysis is it's in the same time domain as EEG, but instead of 128 electrodes, you have like 35,000 different voxels in the head. So you have 35,000 times time. So you have to know when that changed in order to change you would have to record across the session and change your head model or change the electrode positions at different points in the session. Not being done in the HBCD, not usually done in people's labs.
Yeah, okay. And I suppose that, sorry, and then I'll shut up. I suppose impedance changes, I don't know if they'd have any effect, but that is something else that changes, as you know, from the beginning to an end of a study. And I don't know if that's relevant at all to any of these calculations. I can't see how it would be at the top of my head, so to speak, but it might, but I don't know.
So when you measure at the beginning of the session with the EGI protocol,
Yes,
you
correct.
look for you set up a specific criteria of impedance, and you get the impedances of all the electrodes below that,
Yeah.
or you identify electrodes that can't get below that. It's another, you might want to throw those out. The impedance could change over the course of the recording. If you have a 10-minute recording, the water dries out, the electrodes move, they don't touch the scalp in the same way. So at the end of the recording, the impedances could change.
Right.
Good, overly good, really good, excellent recording methods take the impedances at the beginning and then take the impedances at the end, and to make sure that the impedances of the electrodes are still within the correct range. However, there's nothing, the impedances are not used at all in the source analysis. So I'm not sure where they would go, but yeah, that could be an issue. That's really not an issue for source analysis. That's an issue for EEG.
Right, yeah.
So it affects the quality. It doesn't affect it doesn't affect where the electrodes are. It doesn't affect the head model. It doesn't affect the source model. What it affects is the input, the EEG input. So the EEG input becomes less reliable, more noisy, and so forth. So again, that's not really a source analysis issue. That's an EEG issue.
Thanks. Yep.
And one quick comment before, unless this is like directly related, Elizabeth, would be that we do have the videos, so we could capture if there was something like really, like a really big change or something. But again, reviewing, 7,000 videos times multiple visits is not really feasible. But maybe we could add a field for the RAs to add it on the notes. I know many RAs are here, and we hate adding more work for you all, given that all the amazing work that you're doing collecting the data. But maybe something like, did the cap change position significantly or something like that? And then the other piece will be if the visits actually get a lot longer, maybe we should consider adding impedance checks at the end. Good points.
It's, it really, I would opt for the former, not the latter. I'm not sure that recording you could record the impedances there. You could, at the end of the session, you could do all the impedances and add the first ones and second ones, and probably reject channels where the impedances go out of the range. When we're doing this, we have the impedances in the EGI file, and we reject channels where the impedances are too high. And that often happens on electrodes that are bad or electrodes that are not placed properly, and so on. You could have a method where you could have somebody have one of the recorders say, I think there's something wrong with the net placement. And then you could go back and look at the video and see if the net placement changes dramatically enough to justify doing additional analyses. That would be possible.
And without putting burden on the coordinators at the time, that could be something where you get an AI guardian angel sitting on somebody's shoulder, an informed AI guardian angel that could do this work afterwards, and just kind of say, was there a change and how big of a change? And anyway, so maybe post-processing.
Great point.
Dylan, there is some reporting of the quality of the electrode placements. What is that?
Yeah, so I know at UMD, our EEG site team does they look at the photos that the RAs at the site take and they rate how well they capped. So if it's more than like a millimeter away from the Bayesian, then it's no longer excellent, it's good. And then if it moves even more, it's poor. And if it moves, I believe, over 4 or 5 millimeters, it's unusable. So we do kind of have a few fail safes there where we would assume that an excellent placed cap, as measured by our wonderful EEG core, the cap is where we think it is. And then, like, kind of as the capping quality goes down, we have a lot more uncertainty, if that makes sense.
But this is only on the first cap, not at the end of the session or
It's
during
not
the
on the
session.
end. We only have pictures from when they very first put on the EEG. So, like Bill was saying, if we have a fussy baby and they grab the cap as they love to do, we can't really get those movements of the cap, which I think is a problem across all infant and adult studies.
Yeah. Yeah, we've done some studies with children that have like ASD or Fragile X and 12-month-olds. Halfway through the study, we'll be watching them and we'll see their hand go up and go boom. And then it pops back, you know, I mean, the net goes back and we don't do anything about that. We sort of hope that it stayed in the right place, you know, but actually what happens a lot of time when that happens, if they pull the net far enough, the whole net goes off and we don't have any recordings. So we have to quit. But that might be something that, you know, could be added. I think having the site team say something happened during the session to the net placement, and then have, you know, you don't have to do this for every single child, every single session. You'd only look at sessions where there was some dramatic change, and then go back and look at the videos and decide from the video. Maybe half the data is fine and you just take half the data, or maybe you do a second net placement picture from the video if that's possible. So that could be, you could add that. Do you do that, Bill? What do you do when I mean, you have long-term recordings, don't you?
Exactly right. And in those situations, we do the pre and post taking a picture of it, but I don't think we've ever really delved into, you know, some what might be very specific values that have changed as opposed to the overall net. So we haven't taken a lot of time thinking about it until you guys brought this up. I'm thinking, maybe we do have to take a closer look pre and post than what we do right now, rather than eliminating, which is what we do for the most part, electrodes, especially with the preemie babies, because they're moving their heads all over the place. So
Yeah.
I see Elizabeth's.
I think Elizabeth,
is
yeah,
patiently up there. Yes.
Elizabeth
Yeah,
Norton has her hand up somewhere.
yep. Hi. Thank you, John and Dylan, for the talk. Dylan, the tool that you're developing seems so amazingly helpful. And I was thinking about when you were talking about the marking the fiducials, if there's a way for us to collect that data back in so that each research team that uses the tool and uses the data to answer a question in HBCD doesn't have to redo that. And maybe if it could integrate with like the swipes for science that we're using elsewhere in the consortium or something like that, it seems like you've built this beautiful thing, and it would be even better if we didn't have to do it time and again for the same little brains.
I completely agree, and I would love to be able to get something like that set up. I'm kind of working as an independent entity, but if anyone would like to collaborate, or if you have several undergrads that are interested in MRI,
Yeah, I
I
was
think
gonna
that
say,
might be. I'm having
I have
Yeah, so this
many
is
folks who would be glad to help with that. Yeah.
Dylan, I'm not sure if Nathan's on this call, but Dylan and I have been discussing this the last couple of days. It would be nice if that was what every time an EEG recording is done, the people who do the EEG recording take the pictures and then use the pictures to do the fiducial placements. but they have to have the MRI in order to do that. So that probably can't be done at the time of the EEG session. It'd have to be done when you had both the EEG and the MRI. And then those fiducials would become part of the HBCD derivatives or primary data. And 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 that way everybody doesn't have to do them all over again. They're done once and they become part of the system. I think my personal opinion is that you can't really do accurate source analysis without doing those fiducials because they tell you where the net is. And I've showed you a couple of pictures. And if this electrode, which is supposed to be over maybe underneath the prefrontal cortex somewhere, if it's way up here, then the whole set of electrodes is pushed back. So the accuracy of the placements in predicting what type of brain area is gone. If without that kind of information, you can't really do this very well. So everybody should do it. It should be done on every infant that has an MRI. If they don't have an MRI, you could do it on a close MRI. So if you've taken head measurements, you could say, this baby didn't have an MRI, so we're going to use baby number 17532, which has an MRI and has the same size head. And then you do the fiducials on that baby you do the electrode fiducials. So yeah, it should be done. And it should be done on every baby who you ever want to do source analysis, it should be done.
Just a really quick question. The head circumference information is provided by the HBCD as part of their derivatives, correct? Yeah.
So the head circumference measurements are there. So and the reason for that is you can use an infant of about the same age who has a head size that's about the same head size in order to do these analyses. Somebody has a question. Lohith?
Yes. Hi. I wanted to ask about the inverse spatial filters because I'm trying to understand them. They're basically a weighting matrix of all the electrodes across time, right? In order to identify your time period and your electrodes of interest.
So the inverse spatial filter is a set of coefficients that weight the electrodes, and not across time. It weights the electrodes in that space from that lead field matrix. And so if you multiply the EEG times the inverse spatial filter, the input for the EEG is number of electrodes and time. The output, when you multiply that, is number of voxels and time. So it gives you the current activity at the voxels inside the head.
I see. Okay. So it is definitely time localized in terms of looking at analysis for like P3 and 1 certain waveforms.
Loki, maybe we can follow up later. I'm just seeing the time.
Yeah.
We can follow up
Sorry.
separately, and I can connect you with John so that you can understand a little bit more some of the basics of the source analysis. But I just want to take time to say thank you so much to John and Dylan. If there's questions, we can always provide I think there's questions about the slides. John provided the slides so we can make sure that they're for everyone, and then also the recording. So thank you so much, everyone. Our next meeting is July 10th, and actually Elizabeth Norton is going to be presenting on naturalistic paradigms and trial level analysis. So looking forward to that talk as well. So thank you again, John and Dylan. Great talk.
All right. Bye, everybody.
Again. John, are you still there?
Yes, I'm still here.
Thanks